vector projection and vector resolutes. So let's say, we have like two beams, right? Like a wood part and a floor part. And I sort of want to know what the difference is between those two, or how can I break up this wood into two separate sort of vectors, right? So let's say, we have this wood like part and I have the floor, and the wood part is obviously going to cast a shadow, right? It's going to cast a shadow on the floor, right? The sun is above. And we can figure out the shadow and the height of that wood area using vector projections and vector resolutions. So what it actually does is that, just get our laser pointer, is, what vector resolutes asks is, what is that shadow cast by A on the second vector B? So we're trying to find what component of A is parallel to B. Generally, or alternatively, we're trying to break down A into its like parallel and perpendicular components. So ideally, adding U and W will give us A. We're just trying to find those components. The main sort of like question type that comes with this is like shortest perpendicular distance. So yeah, that's what we should be sort of thinking about. Whenever we see, the key term shortest distance or perpendicular distance, we should always be thinking vector resolutes. Earlier today morning, I was answering a question by email. Someone had sent me, they were asking like, was like, how do I know what technique, or how do I know what like topic to apply, when I get a random question. And I was like, thinking about, well, how did I do that? And one of the things I was using was keywords. So shortest distance, I always linked that to perpendicular distance. Whenever you hear shortest or perpendicular distance, you should always be thinking resolutes or vector projections in specialist, especially if it's under like, if it's clearly like a vector topic. Yeah, so you should be thinking of. All right, so the vector resolute of A in the direction of B can be represented by the vector U. And all we do is, what we're doing here is we're finding the magnitude of, finding that magnitude of U, or the magnitude of A, and we're multiplying it in the direction of B effectively. So the way we do that is we take the dot product and then divide it by the dot product squared, and then times that by the direction of B. An alternate way to write this out is, this here is the dot product, so A dot B times the unit vector of B. So B, that there is a unit vector of B effectively. Unit vector of B sort of squared. Okay. Yeah, so that is probably better. So that's really what's happening here. Okay, so just as long as we keep this equation here in our minds, we should be good to go with vector projections and vector resolutes. The scalar resolute is just the size of U. Should have two pipes though. Yeah, that's all there is to that one. You can see, we're just multiplying by this extra element, which is the unit vector, which gives us our direction, like I was saying earlier. So all it is the length of U times the direction of B. I'm just going to put the hat under here, so B hat. Okay. Well, how do we come about this equation? Why is it like that? Well, I think the best way to work this out is via trig. Okay, so we have our angle theta here, right, between our two vectors. I want to try work out what U is, right? I already know what b is, so I just need to work out the magnitude of u, and then after working out the magnitude of u, I can multiply it by the unit vector of b, which gives me its direction, right? So the magnitude of u, well, how would I work that out? Using a, because I don't know what w is. I want to use a to work out the magnitude of u. If you guys remember SOHCAHTOA, that's what I can sort of use here. In this case, it's going to be adjacent over hypotenuse. So I'm going to use cosine theta. So cosine theta is equal to the magnitude of u over a, or the magnitude of a. And so I can multiply this to the other side. So then I have the magnitude of u is equal to a cosine theta. Okay, so how can I, given that I don't know what u is, how can I bring b into this? And the way people thought up was, well, I can multiply both sides of this equation by the magnitude of b divided by the magnitude of b. So I can do this. This is going to be equal to sorry, this is taking me a while to write all of this stuff out, but hopefully it's making sense. All of this is over b, or the magnitude of b. Cool. I just wrote this in just for clarity. Obviously, all of this here is just going to be 1. Technically, this is 1 as well, but what we can do is we can collect this term as a whole. So that becomes a dot b, and that's divided by the magnitude of b. And so that's where we get our scalar resolute from. And the very last thing we have left to do is give it a direction. And to give it the direction, we just use the unit vector of b. So hopefully that makes sense, the way I got around to sort of deriving what the scalar resolute is and then deriving what the vector resolute is. The vector resolute was never a formula I remembered. If I needed it, I could always just derive it. So that's the I guess the benefit of understanding the content really well is whenever you need a bit of content, all you need to do is derive what you need. And to work out what W is, we can just do vector vector addition. So I just subtract U from A and I'll end up with W. Alrighty, I'll let you guys have a go at this one here. I'll give you a couple minutes, not too long, maybe a minute or so, to have a go at this. I'd say just plug it into the formula here. If you do want to have a play around with it, feel free to use first principles and derive it from scratch like I've done here. But just for simplicity, let's just chuck it into the equation. Alrighty. Hopefully that was enough time. So all we have to do really here is just chuck it into our formula here. So first thing I'm going to do is do a dot b. So a dot b is going to be 1 times 1, so 1 So it's going to be 1 times 1 here. So 1 for the I component, plus minus 3 times 0, and 0 times, because remember we have a 0j component here. 0j. So it's going to be 0 times minus 4, so it's going to be plus 0. And for our k component, it's going to be minus 3 times positive 1, which is going to be minus 3. So I'll just write this down. So a dot b. Also, instead of computing it all together, it's a little bit useful to work everything out in smaller bits, which is what I'm going to be doing here. So 1 minus 3, and that's going to give me negative 2. All right, next I want the magnitude of b. So the magnitude of b is going to be equal to 1 plus 4 squared is 16, plus 1, and the square root of this. And this is going to give me 2 plus 16, which is 18. So the square root of that. All right, so now my vector resolute is just going to be square root of 18 times the square root of 18. So 2 over the square root of 18 squared times I minus 4j plus k. And this is going to be 2 over square root of 18 is obviously just 18. Square root of 18 squared is obviously just 18. So it's going to be 2 over 18, which we can simplify to 1 over 9. And what's left is I minus 4j plus k. So yeah, too easy. And we're done. Vector resolutes are probably 2-3 mark questions. So if you can do that pretty quickly and accurately, that's pretty good. Sometimes, in some cases, you would have to fully expand as well, but you don't have to always do that. All right, let's have a go at doing this, and then we'll go into break time. Probably can't do the full 15 minutes in break time, unfortunately, just because, it's 12 already. I'll give you guys a minute or two to do this, and then we'll have a crack. The easiest way, I think, to start this question is to draw it out. Okay, let's get started. This one here is a bit more tough, I think, just because we have to somehow convert this line into a vector. Okay, let's draw out the situation. So we have the point 1 and 2 root 3. So it's probably somewhere here. And our graph is going to pass through 1 over 1 root sorry. It's going to pass over 2 over root 3. I'm just going to quickly rationalize that. So it's going to become root 3 over 3x. Okay, so it's going to be root 3 over 3x. And so it's just going to, probably not going to coincide much with that. So I'm going to assume it goes a bit like this. All right, that's our line. Let's make a unit vector for this here. Well, I mean, we can use unit vectors to define this point. So this point, I'm going to call it P. OP is going to be equal to I plus 2 root 3j. And I need to find this perpendicular distance, right? Because it's the shortest distance. I'm going to find this distance there. Okay. One thing we can do is choose a random point on this curve. So let's say, let's say x equals, I don't know, something cool. Past 1, obviously. Let's just do x is equal to 2. That's going to give me y is equal to 2 over root 3. That's probably not high enough. We'll need something that's greater than 2 root 3, I think, to make it work. Or actually, would it matter? No, I don't think it matters. That graph is just drawn badly. I'm just going to try redraw it. It probably looks a lot more like this. So we're trying to find that distance there. Okay, so this works. So we can create a new vector. I'm going to call it OL, the line, I guess. That's going to be 2i. I could probably, just because I want its distance, just because I want its direction, sorry, I can even use x is equal to 1. It doesn't really matter. So we'll do x is equal to 1. So I plus root 3 over 3j. Let's just use 1. So we'll just cross all of that out. Okay, so let's look at our formula again. So we want to know the dot product first. So we're going to take the dot product between these two. So OL dot OP, that's going to be 1 times 1 for the I component, plus 1 over root 3 times 2 times root 3, which is just going to be 2. And that's going to give me 3. So that's our dot product there. And then what we want is the magnitude of B. So the magnitude of B in this case is going to be 1 plus 1 over 3, the square root of that. And that is going to be 3 plus 1, so it's 4 over 3. That there is all under a square root. So here, that's going to be, I'm going to pull out the 2 from this, so it's going to be 2 square root 1 over 3, or alternatively 2 over square root 3. And then all I need to do here is find that denominator, and to find that denominator I'm just multiplying by twice. So it's going to be 2 over root 3 times 2 over root 3, which is going to be 4 over 3. So right now what we have is 3 divided by 4, which is going to be divided by 3. So that's going to end up as 9 over 4. And obviously we have OL here. And so then the last step is just to combine everything. So I plus, oh, actually we don't even need to go that far. Okay, doesn't matter too much, I think. Um, hmm. Sorry, I'm just thinking about this. Yeah, actually, I think we can stop at this point here. Because what this here, we don't, we just need to figure out, we just need to figure out what the scalar resolute is. And that's going to be 9/4. And now, what's nifty is we can use Pythagoras theorem, right? So we have 9/4 here. Um, and now all we really need to do is find the magnitude of this, which is going to be 1 plus 12, because that's going to be 4 times 3. Square root of that is 13. So now what we have here, so square root of 13, we have a triangle like this. We want to find the shortest distance, right? We know this side is 9/4. Sorry, that's a dividing line. And we know this side is square root of 13. So what we need to do is just Pythag, really. So this is going to be, so right at the top, 13 minus, that is going to be 81 divided by 16. Square root of that should give us our answer. I've probably made some mistake here in the maths, but the general idea is the same. We want to choose some vector on this line. So the easiest way to do that is plug in, 1 and find your y coordinate. Create a set of 2 vectors, and then use that to find the scalar resolute, and then you can use Pythagoras theorem to find out the perpendicular distances. Alternatively, you can find out the vector resolute and then get your original vector and subtract it from your found vector resolute, and we'll get this.